heating of glycerin in a multipass heat exchanger. So previously we already done the counterflow heat exchanger, which is a condenser. So for your information, counterflow and parallel flow does not need correction factor. Okay, that equation Q dot equal to U AS delta T log mean will not have any correction factor, since that equation derived from the parallel flow equation. So you may refer to the previous video about the counterflow and parallel flow. But the problem is when we deal with multipass heat exchanger or cross flow. So multipass heat exchanger, for example, shell and tube heat exchanger, and the other one for the cross flow is such as radiators, is one of the types of the cross flow, okay, heat exchanger. So now we focus more on the multipass heat exchanger. So two shell passes, 4, 6 tube passes, or one shell passes, 2 tube passes. So that is multipass heat exchanger. So let's take a look at the question. A 2 shell passes and 4 tube passes heat exchanger is used to heat glycerin. So from 20 degrees Celsius to 50 degrees Celsius by hot water, which means that the glycerin being heated up and the energy comes from the hot water. So the glycerin will be heated from 20 degrees Celsius up to 50 degrees Celsius. Okay, now we take a look at the information which enters the thin wall 2 centimeter diameter tubes. So which means that the hot water is flows inside the tubes. Okay, so that definition, that statement is for the hot water. So hot water enters thin wall 2 centimeter diameter tubes. Okay, so hot water will be in tubes, and tubes at 80 degrees Celsius, and hot water enters to the tubes at 80 degrees Celsius and leaves at 40 degrees Celsius. Okay, we have pH in and pH out, and also we have TC in and TC out. So all the information about the temperature has already been given in the question, which means this question can be solved by using LMTD method. If one of the temperature is not being given, normally temperature exit will not be given in the question for the NTU method. So if that's the case, then you have to use NTU method. Now, all the information about the temperatures is already been given, and then you can use LMTD method in order to solve this question. So that is our first decision. We will use LMTD method. Now we have to take a look at all the information, and then we can finalize our decision. Okay. The total length of the tubes in the heat exchanger is 60 meter. Okay, we have the total length of the tubes is 60 meter, and then the convection heat transfer coefficient, okay, is 25 watt per meter square K on the glycerin. So the shell side heat transfer coefficient is already been given, okay, and then 160 watt per meter square Kelvin on the water tube side. So both of the heat transfer coefficient is already been given, which means, so as I mentioned before, the chapter 4 is the combinations of all the chapters, all the previous chapters learned by you, okay? So chapter 1, 2, 3 will be combined, and it will be been tested in this chapter 4. Now, for if all this information about the glycerin, specifically for the heat transfer coefficient, glycerin and water is already been given for the convection heat transfer coefficient, which means that you may not need to find, and you may not need, or you may remove, or you may omit the method of internal force convection and the external force convection. Why? Because these two chapters is only focusing more on how to calculate what is the convection heat transfer coefficient for the external and internal force convection. Now both of them in this question, both of them are already been given. So you have you will not need to find what is the H for both of the side lah. Okay, external and internal. Okay, now that means the rate of heat transfer in the heat exchanger, A, before any fouling, and B, after fouling, with a fouling factor of 0.006 meter squared Kelvin per watt, occurs on the outer surfaces of the tubes. So that is the questions. Then we have to decide whether this method is LMTD or NTU methods. So based on the information given, and there is no specific request by this question, you may use either either LMTD method or NTU method. Now I will use LMTD method, since the LMTD method is much more not so complex compared to the NTU methods. So I will use LMTD method in order for me and for you. I will teach you in order for us to solve this question. So this is the figure. Okay, we have the hot water into the shell, into the tube side. So this is tube side. So the hot water will be entered at 80 degrees Celsius and leaves at 40 degrees Celsius. For the cold water, which is this hot water, is purposely to heat the glycerin up to 50 degrees Celsius from 20 degrees Celsius. So the cold water of the glycerin will be entered. So the arrangement of this heat exchanger will be in the counter flow. Okay, multipass counter flow. So counter flow, which means that when here is hot water in, therefore this is TC out. Cold glycerin will be out here, and then for the hot water out is 40 degrees Celsius, and the cold water glycerin will be enters. Okay, this is counter flow. Okay, multipass counter flow. Okay, so from a previous video, I've already shown you this graph. Okay, we have 4 different types of graph here. So first is 1 shell pass, 2, 4, 6 tube passes, and then the second one is 2 shell passes and 4, 8, 12 tube passes. For the fourth, single pass cross flow with both fluid unmixed, and third and fourth is single pass cross flow with one fluid mixed and the other is unmixed. Okay, for the C and D is for the cross flow, whereas for A and B is multipass flow. Okay, so now our question is for multipass flow. Okay, multipass heat exchanger. So what we have to do is we have to refer A and B only. We are not referring to C and D because C and D is cross flow. So let's take a look at A and B. So in order for you to determine whether you have to use A or you have to use B, please refer to your question. So your question shows us 2 shell passes and 4 tube passes, which means you have to refer 2 shell passes. Now take a look at this figure, this chart, this graph. So A is for 1 shell passes. Is it A? No. Okay, we have to use B because B is 2 shell passes, 4, 8, 12 tube passes. Okay, so I'm really sorry because this figure is for 1 shell pass and 2, 4, 6. Okay, So you will refer to this figure. Why do we have to refer to this figure? Take a look at this graph. So this part, correction factors, that is our aim. Why? Because previously we know that the derivations of Q dot equal to the derivation for delta log mean is only for counter flow or parallel flow, and it is based on the parallel flow, based on the counter flow. So the derivations is for these two types of heat exchanger. But now we have multipass. So what we have to do is we have to include correction factor. So previously we know that the Q dot is UAS delta T log mean. Now this is for the cross flow and the parallel flow. So what if we have multipass and cross flow? We counter. So counter flow and parallel flow. So what if we have multipass and cross flow? So we have to include the correction factor to this delta log mean in order for us to correct the value of delta log mean. Therefore, you will have UA as F. This is F and delta T log mean. This F represents correction factor. So this is what you have to do. This equation is for multipass, heat exchanger, and then cross flow. So cross flow heat exchanger and multipass heat exchanger, you have to include the correction factor. That's why you have to refer to this figure, okay, to find what is the correction factor here, F. So I've already teach you on how to refer to this figure. So we have two different values needs to be calculated before you refer to this figure. The first value is R value and the second value is P value. From here, you have not to worry so much because this figure is included with this kinds of equation. So you refer to this figure, you will see this equation. So here I will explain a little bit more on the R value. So we have uppercase T and lowercase t, small case and uppercase, okay? Capital letter and small case of t. So for the capital letter T, this is referred to the shell side temperature, okay? Shell side temperature, and then T refers to the tube side, okay? Tube side temperature. Okay, so I change the color first. Okay, from here you have to substitute the value for the temperature inlet. T1 refers to inlet temperature and T2 refers to outlet temperature. So you have to, or maybe you blur when you during the examination, and you can refer to this figure because this figure is already located where is the location of T1 and T2. So from here we know that T1 is inlet temperature for the tube side for the uppercase T, and then lowercase T1 is for the inlet temperature for the tube side, okay? So that is the equation that will be used in order for you to find what is the correction factor. After you get R value and P value, you have to refer to this figure. So P value is here. So refer to this below, and then you have to take, for example, you have 0.4, and then you have to drag straight line up to 1, and then you have to refer to R. For example, your R is your R is 1.5. So find the points of intersection, and then you will drag your point up to this correction factor. So you have to refer to this line. 1.5 is represent for this line, okay? 2.0 is this line. What if the values of R is in between? You have to interpolate. Okay, you have to interpolate to find what is the point of intersection between these two. Okay, so this is the figure of this question. So now we take a look at the first question, A, before any fouling. So which means we have to determine what is the rate of heat transfer in heat exchanger. So since this is the combination of chapter 1, 2, 3, so we have to take a look at this point. Okay, you may select any point, but I take here and I will enlarge this figure, and then I will make this is our tubes, and then there is a fluid outside, shell side, and there is a fluid inside. Okay, this is hot fluid, and then the outside of this is a cool fluid. So what we have to do here, since this is combination, you have to follow and you have to do these kinds of steps in order to analyze the heat exchanger. Okay, so what is the point of you doing this? Because you have to find what is the U. So now we know that we have to find what is the rate of heat transfer, UAS F delta T log mean. So now we have U, overall heat transfer coefficient. What has been given in this question is only heat transfer coefficient. Okay, for external shell side and internal tube side. But now we have to find what is the overall heat transfer coefficient. So we know that when we have to calculate what is the overall heat transfer coefficient, we have to find the total resistance in the tubes to the outside. So here, the hot water, the heat transfer will transfer from hot water to cold water. So this is Q dot. Okay, so you have to find what is the total resistance of these problems. So now we draw a thermal resistance network. So from tube inside, okay, T1, for example, T1 is represent hot water, hot fluid temperature. Then after that, it will transfer to this side, right, Di. So we have resistance 1, which is R convection 1, and then from this point we have conduction. So we have conduction, R conduction, and then after that we will have convection, okay, on the surface of the outside surface of the tubes. Okay, so we have last one is convection, so R convection 2. So this is the thermal resistance networks for your tubes. Okay, now what we have to do, we have to refer to this, or we have to refer to the question. Is there any information given that you will omit some of these resistance or some of these resistance, okay, or one or two resistance? Now take a look at this statement, which enters a thin wall. Okay, thin wall, which means that wall is too thin. And as I mentioned before, when there is a thin wall, therefore we can, yes, omit the R conduction. So now your thermal resistance network will be simplified into two only. So we have T1, R convection 1, and R convection 2. So let's say this T1 is represented from the inside of this tube, and then T2 is for the shell side. So now we only have two types of convection. one types of convection, one types of modes of heat transfer, but at two different locations, internal and external. So from this question, we know that the heat transfer coefficient is already been given in this question. So where we have the glycerin side for the shell side is T2 here is CF, cold fluid is a glycerin fluid, therefore the H for the H, this is H2 and H1. So H2 is for the shell side, and then H1 is for the tube side. So now we already have shell side and tube side heat transfer coefficient, convection heat transfer coefficient. So we may not need to find what is the heat transfer coefficient. As you can refer and recall from the previous, in the chapters 3, you have to do some of the calculation in order for you to determine what is the heat transfer coefficient based on the Nusselt number. Okay, now what we have to do is we have to calculate what is the overall heat transfer coefficient. Since we are only have two types of resistance in this question, so let's calculate what is the overall heat transfer coefficient. So overall heat transfer coefficient, we know that 1 over U is 1 over Hi plus 1 over H out. So this is the equation to determine what is the overall heat transfer coefficient. Then in order for you to determine what is the overall heat transfer coefficient, you have to rearrange this equation, and it will becomes 1 over Hi over 1 over H out. So substitute all the values given in the question, and you will get that this value, so 1 over 160 plus 1 over 25. So you will get this value is 21.6 watt per meter square dot Kelvin. This is your overall heat transfer coefficient. Now, so we already solved for the overall heat transfer coefficient. Okay, now we have to find what is the surface area, ES. So how to find the ES? So since surface area, for the surface area we will not use, we have two different types of equation for the area. Pi d squared over 4, and area is pi dl. So this area is to find the cross-sectional area. Okay, area. So for this is for surface area. Okay, cross-sectional areas normally you will find for the mass flow rate. Okay, surface area is for Q dot. So now we will use AS. So here is AS and here is AC, A cross-sectional. Then we will use AS in order for us to determine what is the total surface area of this question. So AS is equal to pi. What is the diameter of this tube? So since this is thin wall, so you will plug in the value of 2 centimeter diameter tubes. So if there is no words or any statements that mention that this tube is thin wall, therefore you have to take the diameter at the outside. Okay, d out. Since d out for external and di for the internal. So since this is thin wall, both of the diameters is the same. So you will plug in the 2 centimeter diameter value. Okay, 2 centimeter value. So your diameter is 2 times 10 to the power of minus 2 meter times with the length of your tube is 60 meter. 60, yeah? So you will get the value for the AS is 3.77 meters squared. Okay, this is your area. So now what we have to do, we already calculate the value for the overall heat transfer coefficient and then AS. So now, since this is multipass heat exchanger, we have to find what is the F, correction factors. How to find what is the correction? How to find the correction factors? From the correction factors, from this equation, we can find the correction factors based on the R and P values. So hold on that part. I will focus to the delta T log mean. So let's take a look at delta T log mean first. Okay, so for the delta T log mean, I will find what is delta T log mean. So we have to find what is delta T1 and delta T2. We have to subtract and then ln delta T1 divided by delta T2. This is the equation for delta log mean. So this is for the counter flow. But now we have multipass cross flow. We have to provide another info and another values in the delta T log mean, which is correction factors. So that correction factors will be calculated after this. So we have to solve this delta T log mean first. So delta T1 is TH in, TH in minus TC out. TC out, and then delta T2 is T H out minus TC. Okay. Now we can refer this into from this figure lah. Okay. So actually delta T1 is up to you whether you want to use this as a delta T1 or this as a delta T1. So it is up to you. Okay. So you have to minus biggest value or the high value to the lower value. Okay. 40 minus 20 and 80 minus 50. Okay. So it is up to you whether that delta T1, it can be changed, depends on you. Okay, so your delta T1 is 80 minus 50, so this is degree Celsius, and then the second one is 40 minus 20, 40 minus 20 degrees Celsius. So you will get its value is 30 degrees Celsius for delta T1 and 20 degrees Celsius for delta T2. So to find what is delta T log mean, since this delta T log mean is for the counter flow, therefore I will put CF here. Counter flow equal to, so substitute all the values, 30 minus 20 divide by ln 30 divided by 20. So you will get your delta T log mean for CF is 24.7 degrees Celsius. So you already calculated your delta T log mean for counter flow. So here, this equation is actually delta T log mean for CF. So now we have determined this. What we have to do now is we have to find what is the friction coefficient factor. Since we have to correct the value from the counter flow delta T log mean, okay, we have to provide the correction factor. How to find the correction factor? From this figure. So from this figure, you have to find what is the R value and P value, and therefore we have to find these two values first. So for the R value, for the P value, so we know that the P is, the equation is T2 minus T1 for the tube side, and then T1 shell side minus T1. So we calculate this first. 40 for the tube side of outlet, T2 is tube's outlet temperature minus, so T1 is temperature for the tube's inlet, and this is active, divided by, so T1 is, this T is for the shell side inlet. So shell side inlet is 20 degree minus this is tube inlet. So the tube inlet is 80. So you will get that value for the P is 0.67. Okay, for the R value, okay, tube side, shell side minus shell side 1 inlet and minus outlet divided by tube outlet minus tube inlet temperature. So 20 minus 50 divided by 40 minus 80. So you will get the value for this is 0.75. So we already get both of these values, P and R. So what we have to do, you have to refer to this figure, okay, this figure. So your value for the P is 0.67, maybe here, I just predict, this is just assumption, okay, 8, 7, this is 5, maybe here. So you have to draw a straight line up to 1. So straight line, straight line, and then your R value is 0.75. 0.75 is in between 0.6 and 0.8. So here, so you have to interpolate here, or maybe you can predict here where is the location of the 0.75, and then you make it the point of intersection, and then you track to this point. So you will get what is the correction factors. So from here, I get the correction factor for this P and R value is, my correction factor is 0.91. Okay. Again, refer to the right chart. Okay, 2 shell passes and 4 tube passes. Okay. So do not refer to 1 shell passes. Refer to 2 shell passes. So 0.91. So we already have all the information in order for us to determine what is the Q dot here. So before fouling, okay. So now for the Q dot, the equation is overall heat transfer coefficient times with total surface area times with correction factor times with delta T log mean counter flow. Okay, substitute all the values. So 21.6. I'm really sorry because I will not put the unit since it will take time. So 3.77 and then times with 0.9. Okay, 0.91, sorry, and then 24.7. So you will get the rate of heat transfer is 1830 watt. So during the calculation here, if you do not put the unit, is still okay, but the last here must have a unit. So if you do not have the units, then we do not know what kinds of value that this what kinds of unit that this value represents for. Okay, so this value is for the Q dot. Okay, 1830 before fouling. So you have to remember that this value is before fouling. So what if there is a fouling inside the shell and tube? This shell and tube, this question. So when there is a fouling inside the heat exchanger, what will happen? What will change? Yes, the resistance will change. It will create more resistance. Therefore, the rate of heat transfer of heat transfer will be affected. So you have to find what is the overall heat transfer, new overall heat transfer. Since we have fouling on one of the surface of the heat exchanger. So for the fouling, so we have fouling. If there is a fouling, therefore you will increase the resistance and it will affect the rate of heat transfer. Okay, so we have to find what is the new overall heat transfer coefficient. You knew because we have fouling inside the reactor, inside the heat exchanger. So 1 over 1 per 1 HI plus 1 over H out plus we have R F. So this is fouling. So substitute all the values, you will get this value is 21.3 watt per meter square dot Kelvin. So from here, we have to substitute into Q dot U as F delta T log min CF. So do we need to calculate what is the ES, F, and delta T log min? No need. The only affected areas or the only affected values if there is a fouling is only U. So you have to calculate what is the new overall heat transfer coefficient. Then you have to substitute into this equation. 21.3 times with 3.77 your AS times with 0.91 for your F, and then delta T log min is 24.7. So you calculate this, you will get your value of heat transfer, rate of heat transfer will be 1805 watt. So as you can see, reduce up to 25 watt. So if there is a fouling inside this heat exchanger. So that's all for the LMTD for the example 11. Then thank you.